Today, in classical mechanics, we are going to start a very important concept, and this is the concept of a scattering in a central force field. You know, the problem of scattering of particles at atomic scale is in a central force field is extremely important problem in modern physics. Definitely, we have studied the scattering of a beam of protons or alpha particles by the atomic nuclei of a target, and this is just a very interesting problem in nuclear physics. Of course, the problem in quantum mechanics, the problem is actually quantum mechanical, but it can be dealt classically too, because the procedures for dealing the scattering problem in classical as well as in quantum mechanics are similar. Further, a classical study of a scattering problem gives a chance to the beginner to learn the language of problem. So actually, the actual process of handling such a problem is quantum mechanical, but at the same time we can handle the problem in classical way. And as I have told you, if you are a beginners for the scattering problem, first of all you have to learn about the classical treatment of this problem, and then you can understand in a better way the quantum mechanical treatment of such type of problems. So these type of problems we study in quantum mechanics, in nuclear physics, and also in classical mechanics. Our present concern is classical mechanics. So actually in this scattering problem, first of all, we will learn about the basic fundamentals of the scattering problem. We will learn about this, what is a scattering cross section, what is differential scattering cross section, and total scattering cross section. And we will also see what is angle of scattering, what is impact parameter, and how they are related. These are the basic fundamentals of this problem. And after knowing these basic fundamentals, then finally we will discuss the Rutherford alpha scattering experiment, but on the basis of classical theory, not quantum. We will not treat the problem quantum mechanically. When we will study the same problem in quantum mechanics or in nuclear physics, there you will find the quantum mechanical treatment of the same problem. But as our present concern is of classical mechanics, so we will handle this problem of Rutherford scattering by the classical concept. Okay. So let us see, first of all, what is this scattering process, how the different terms related to this scattering process will be defined. And for this, let us consider, you can see this figure, that a uniform beam of particles incident on a center of force. As you can see that this small sphere which I have shown here, this represents the scattering center, or you can say this is the center of a scattering. Okay. And this parallel lines marked by these arrowheads represent the beam of incident particles. We also assume that all the particles of the beam are of equal masses and equal energy. We consider it. It means mass of each particle of the beam are same and their energy is also same. Okay. Now we will define the intensity of the incident beam, and we will denote it by the symbol I naught. What is this intensity? Actually, the intensity of the incident beam I naught is the number of particles crossing unit area per unit time normal to the direction of the beam. Okay, you can see I have mentioned here what is this I naught. I naught is the number of particles crossing unit area per unit time normal to the direction of the beam. Okay. So, this is also called intensity of the incident beam, okay, or this is also called incident flux density. So I naught, which represents the number of particles passing through unit area in unit time in a direction normal to the beam, that is actually the measure of intensity of the incident beam, which is also called incident flux density. Okay, incident flux density. Now, we assume that the incident beam experiences a force due to this scattering center, and this is of the central force origin, because our present concern is scattering in central force field. So you can think that this scattering center will provide a force acting on the incident beam of particle, and that force is a central force. And you know, a central force is distance dependent. Here we assume that as the distance between the incident particle and the scattering center becomes infinite, the force of interaction between the scattering center and the incident particle falls off to zero. We consider it. For example, if we are talking about the scattering of alpha particle, you know, alpha particle is incident on a nucleus. Nucleus has positive charge. Alpha particle has also positive charge, and so between the nucleus and the alpha particle, Coulombian repulsion takes place. And you know that Coulombian force is actually a central force, and it is repulsive. Okay, and this Coulombian force is inversely proportional to R square, where R is the separation between the interacting particle, that is alpha particle, and the target nucleus. Okay, so you can see if R will tend to infinity, this F will tend to 0. Okay, F will tend to 0. So we consider in general that when the particle approaches the center of force, it will interact with the center of force. For example, as I have told you, an alpha particle which has positive charge will experience a repulsion from the positively charged nucleus, and so that the path of the alpha particle or incident particle will get deviated due to this repulsion. Okay, the original path was actually a straight line, and due to the repulsion, the path will get deviated. As you can see that this path I have shown here, this is actually the deviated part of the incident beam. These two paths have been shown here, which has been deviated from the original direction by an angle phi. You can see it here. Actually, this angle phi with which the incident beam of particle gets deviated from its original direction, that is called angle of scattering. So here, this phi is actually called the angle of scattering. Okay, so you can define the angle of scattering in this way, that it is the angle between the incident direction and the scattered direction. Okay, angle between incident direction and the scattered direction, that is actually called the angle of scattering. Okay, so this is and this phenomenon of deviation of a beam of particle due to the interaction with the center of scattering, this phenomenon is actually called a scattering of particles. Okay, a scattering of particles. As I have told you earlier, that the concern of my present lecture is what? Its concern is only to know about the basic fundamentals which will be needed to deal with the problem of scattering of alpha particles, which the experiment which was performed by Rutherford. And in this regard, first of all, we will have to know about the scattering cross section. What is this scattering cross section? First of all, we will know. Okay, And for knowing the concept of a scattering cross section, let us consider that this uniform beam of particles moving with flux density I naught, as we have considered, I naught is incident on a target. Okay, and we consider that in the target there is an effective area, let us say this d sigma. D sigma is the effective area of the target, let us consider. And we consider that this d sigma is the area of the target on which whatever the alpha particle or the beam of particle will incident, that gets scattered into a solid angle of d omega, into a solid angle of d omega. It means if you consider that n particles are incident on this area d sigma, then all these n particles will be scattered into a solid angle d omega. We consider it. Okay, as I have mentioned it here, you can see, consider a uniform beam of particles moving with flux I naught particles per unit area towards a scattering center. Imagine the scattering center possesses an area d sigma perpendicular to the path of the beam, such that whatever particles hit this sigma area are scattered into a solid angle d omega. Okay. Now, as you know that this I naught, which is incident flux density, that is actually the number of particles incident per unit area per unit time. Since on unit area the number of incident particle is I naught, so what will be the number of particles incident on this d sigma area? That will be simply I naught d sigma. And as you have considered that the total number of particles which are incident on this d sigma area, that is scattered into a solid angle of d omega. So you can say that the number of particles scattered into d omega solid angle per second, that will be equal to I naught into d sigma. I naught into d sigma. I think you have definitely understand how this I naught d sigma represents the number of particles scattered into a solid angle d omega per second. Okay. Now we consider that this I omega, this is capital omega. This I omega, let us consider, this is intensity of the scattered particles. When you say this is intensity of scattered particles, what does it mean? It means this is the number of particles scattered in a direction omega per unit solid angle per unit time. Okay, that is the number, that is called intensity. Okay, and if I omega represents the number of particles which is actually scattered through unit solid angle in unit time, then if you want to know what will be the number of particles scattered into a solid angle of d omega, what will be that? Since through unit solid angle the number of particles get scattered is I omega, okay, and so through this d omega angle the number of particles scattered will be I omega times d omega. Okay. But you have learnt that whatever the particle is incident on this angle d sigma, this area d sigma, all those particles get scattered into the solid angle d omega. So definitely this I naught d sigma will be equal to this I omega d sigma, because these are the number of particles incident on this area d sigma, and all those particles get scattered into d omega. And we have calculated that if I is the intensity of a scattered beam of particle, then I omega d omega is the number of particles scattered into the solid angle d omega. So I naught d sigma will be equal to I omega d omega. Okay. So you can see, I have written here that the number of particles scattered into the solid angle d omega will be this much. This is I omega d omega. Okay. And both of these values will be equal. So I have equated here. You can see this I naught d sigma will be equal to I omega d omega. And so you can see from here that d sigma by d omega will be equal to I omega divided by I naught. I omega divided by I naught. Now, this quantity d sigma by d omega, this is actually represented by the symbol sigma omega, and it is called differential scattering cross section. This is known as differential scattering cross section, or it is also simply called a scattering cross section for a scattering in this omega direction. Okay. So you can say that this differential scattering cross section, which we denote by the symbol sigma of omega, and which is equal to d sigma by d omega, that is equal to I omega over I naught. Now think about the dimension or unit of this differential scattering cross section. You know that the dimension of this d sigma, which represents area, is actually what? This is actually meter square. Okay. And d omega, which represents the solid angle, which is a dimensionless quantity. Solid angle is dimensionless. So you can say that the dimension of this sigma omega is actually equal to dimension of length, dimension of area. And that's why the term cross section is used. Why it is called differential scattering cross section? Why cross section? Cross section is due to its dimension is equal to the dimension of area, hence this quantity is called cross section. Okay. You can also check this dimension by this ratio I over I naught. I, you know, this is number of particles passing through unit solid angle in unit time. So it's a unit of I will be simply per second, or you can say second inverse. Okay. But I naught represents the number of particles passing through unit area in unit time. Unit area in unit time. So its unit will be meter minus 2 second inverse. And this second inverse will cancel out, and this will be meter square. And so you can say that the dimension of this sigma omega is that is same as that of the dimension of area, and that's why it is called a scattering cross section. Okay. I think you have clearly understand why the term cross section is used here. Okay. And on the basis of this equation 4, now you can easily define what is this differential scattering cross section. You can define it as a ratio of the intensity of a scattered beam of particles and the incident flux density. I omega is the intensity of a scattered beam of particles, and I naught is the incident flux density. So the ratio of the ratio of the scattered beam of particles and the incident flux density, that is equal to the differential scattering cross section. Or in other words, you can say it is ratio of the number of particles scattered in omega direction per second per unit solid angle to the number of particles particles incident on unit area of the target per second. Okay. So this is the basic definition of the differential scattering cross section, and I hope you have clearly understand what is this differential scattering cross section, why it is called cross section. I think all these facts has been now clear to you. Okay. Now, after getting the idea of differential scattering cross section, now we will define what is total scattering cross section. You know, if you are talking about the total scattering cross section, that will be simply the integral of the differential scattering cross section. So if you denote the total scattering cross section by the symbol sigma, that will be what? That will be integral of the differential scattering cross section with respect to the solid angle. So sigma, which is total scattering cross section, is equal to integral of sigma omega d omega. And you know this sigma omega is equal to d sigma by d omega. So this sigma will be equal to integral of d sigma by d omega d omega. This is the equation using which you can easily find the total scattering cross section if you know the differential scattering cross section. Okay. So after this section, I think your concept regarding the differential scattering cross section and the total scattering cross section is now very clear to you. Okay. Now we will define another important term, which is called a scattering angle. As I have told you earlier, that this scattering angle is the angle between the incident direction of the particle and its scattered direction. As you can see, I have shown in that figure that actually the incident direction has been considered in this direction x. Okay. And the particle after scattering, you can see, makes an angle phi with this incident direction. So this angle phi, which is the angle between the scattered direction of particle and the incident direction of particle, that is denoted by the symbol phi, and that angle is called angle of scattering. Okay. So I have mentioned it here that it is the angle between the incident and the scattered direction of particles, and it is denoted by phi. Okay. Now we will see another important term, which is called impact parameter. Actually, impact parameter plays a very important role in dealing with the problem of scattering. Okay. What is this impact parameter? Actually, this impact parameter is defined as the shortest distance or the perpendicular distance between the incident particle and the target or a scattering center. Let us see. If you consider that this is our scattering center, you can say this is nucleus, and we project an alpha particle towards this nucleus. As you know, due to the interaction, Coulombian interaction or Coulombian repulsive interaction, this alpha particle will get scattered. Okay. And if you will draw a normal from this scattering center to the incident direction of the particle. This is your incident direction. So this will be the normal distance or perpendicular distance or the shortest distance, because you know the perpendicular distance is the shortest distance. So if this shortest distance or perpendicular distance of the incident direction of particle from the scattering center, this is called impact parameter. Actually, this is the distance by which the collision misses to be one-dimensional or head-on. If this P will be 0, then the projectile will hit the target directly. Collision will be head-on. But if P is not equal to 0, the collision is two-dimensional. After scattering, the particle will move in a plane, and So collision will be not head on. So you can say that P is the minimum distance by which head on collision is missed. This is the minimum distance by which the head on collision is missed. Okay. Now here we will see, you can see this figure. First of all, we consider that the beam of particle which will incident on an area lying between this P and P plus dP. P and P plus dP. This annular ring represents the area which is actually between the rings of radius P and P plus dP. And we consider that the beam of particle incident on that very area gets scattered between phi and phi plus d phi. Phi and phi plus d phi. It means you can say that when the impact parameter is P, then the angle of scattering is phi, and when the impact parameter is P plus dP, then the angle of scattering will be phi plus d phi. Actually here this plus sign will be actually minus sign, because with increase in P you will see phi will decrease. So I have written here plus, but actually the value of d phi will be then minus, because with increase in P this phi will decrease. Okay. Now actually this particles scattered from those that area will move into a solid angle, and that solid angle will be what? You can see the figure. See this figure. Actually I have shown that the angle of scattering, when it is phi and phi plus d phi, it means you are considering that the particles which are incident on an annular ring of the target between P and P plus dP, those particles get scattered at an angle of scattering between phi and phi plus d phi. And all those particles actually subtend, or all those particles are content in a solid angle d omega, and actually that d omega will be what? See here, I have shown here this annular ring, and the distance of this periphery of this annular ring from the scattering center has been assumed r. Okay. So the inner radius of this ring will be r sin phi. You can check it. Sin phi will be equal to this radius divided by r. So radius will be r sin phi. And its width, this is its width, and this width will be what? From the relation d phi equal to width of the ring and divided by r. So width will be r d phi. So this width is r d phi. Okay. And so you can say that the particles which are incident on this area between pi and pi, area between pi p square and pi p plus dp whole square, pi times p plus dp square minus pi p square. The particles passing through this area will actually scattered between the angle phi and phi plus d phi, and that will be content in a solid angle d omega, and that solid angle will be made by this annular ring which I have shown here at the scattering center. So what will be actually that solid angle and the number of particles you can see. Solid angle, you know from the definition of solid angle, that is area divided by r square, ds by r square. And what will be the area of this annular ring? You can see this area will be its circumference, and the circumference will be 2 pi r sine phi. This is its circumference, and its width is r d phi. Okay, so 2 pi r sine phi r d phi, this is its area, and divided by r square. Now this r square will cancel out, and the angle of solid angle subtended by it is 2 pi sine phi d phi. Okay. Now the number of particles incident number of incident particles crossing through this area d sigma, which is equal to 2 pi p into dp, 2 pi p into dp, and this area is actually the area lying between the rings of radius p and p plus dp. Okay, so what is the total number of particles which is incident on it? As you know, the incident flux density is I naught, which means the number of particles incident per second on unit area is I naught. So on d sigma area, the number of incident particle will be I naught d sigma, but d sigma is equal to 2 pi p into dp. So this is I naught 2 pi p dp. Okay. And as you have learnt earlier, that this number I naught d sigma, this is equal to I omega d omega. You have learnt earlier. I omega is the intensity of a scattered beam of particles, and d omega is the solid angle in which the scattered particles are content. Okay. Now you can see this d sigma, since you know sigma omega is defined by d sigma by d omega. Okay, d sigma by d omega. This is d omega. This is d omega. So d sigma will be sigma into d omega. So I have written here, instead of this d sigma, sigma omega d omega. Okay. But you have calculated here this d omega, this is 2 pi sine phi d phi. So let us substitute it here. So I omega d omega equal to I naught sigma phi 2 pi sine phi d phi. Okay. And from here we can find the value of this p. See here. I naught d sigma. D sigma, you know, d sigma is equal to 2 pi p d pi. So this I naught into d sigma, d instead of d sigma I have written here 2 pi p d pi. And that will be equal to this much. Here minus sign has been used. This is the result, but now we have used minus sign. Why? Because you know how this p and phi are related. As I have told you earlier, that when the value of p increases, the impact parameter increases, the value of phi decreases. So if you will take dp positive, then you have to take d phi negative. But the sign should be positive. So when you will take minus sign, then after taking d phi negative, the result will become positive. And that's why we use here the minus sign. So this negative sign is introduced because an increase of p will decrease phi. Okay. So I naught 2 pi p dp, this is equal to I naught sigma phi 2 pi sin phi d phi. Okay. And here this 2 pi will cancel out, and this I naught also cancels, and so you can find this sigma phi, which is actually the differential scattering cross section, in the direction phi, you can say, and this will be equal to minus p over sine phi dp by dy. Okay, and you can see from this result that actually the differential scattering cross section in the scattering direction phi depends on the impact parameter. So this equation actually indicates the dependence of the differential scattering cross section on the scattering angle phi, how they are actually related to one another. So this is a very important equation which relates the differential scattering cross section and the impact parameter. Okay. So in this lecture you have learned about these basic fundamentals, but our prime aim is to deal with the problem of Rutherford alpha scattering, but classical treatment, not by quantum mechanical treatment. Quantum mechanical treatment you learn in your course on nuclear physics and in quantum mechanics, but here in classical mechanics this Rutherford scattering will be treated classically. So wait for my next lecture on Rutherford scattering, which will come very soon. Thank you very much.